All right, so we don't have a whole lot left. Um, just a couple of points to talk about, and then the most of the rest of the chapter 21 here is really interesting. It's stuff that I'm certainly not going to test you on tomorrow, um, and you probably might never actually see a test question on it anywhere in your careers. But at the same time, there is some interesting stuff in there in terms of, what happens inside of our sun, uh, how we use some of this information to do things like radioactive imaging or um, uh, carbon dating, those kinds of things. And so I encourage you that if you're interested in that kind of stuff, or if you're going into a medical field or something like that, you might want to just give that a little bit of a look over. But you're not going to see anything tomorrow on the final exam as far as that's concerned. Um, to that end, let's finish up here and talk about gamma radiation. Now, gamma radiation is a type of radiation that does not emit particles. So, in all of the other ones that we looked at, the alpha decay, the beta decay, the positron emission, the electron capture, a particle was always involved in those in some kind of way. Either the particle was emitted along with the energy, or the particle was absorbed and a bunch of energy was released in the process. With gamma radiation, what we see is just a big bundle of energy. And so, um, gamma rays are high energy electromagnetic radiation. They come about as a result of annihilation reactions. What an annihilation reaction is when we have two particles that are basically antimatter of each other. So in this case, a positron and a negatron or a beta particle, when they collide with each other, they collide and basically the charges annihilate each other. They wipe each other out. And we get a massive burst of energy emitted as a result. That burst of energy has practically no mass. Where we see this most often is that it is generated in stars. So this kind of reaction tends to occur in stars, in the core of stars, as fusion reactions are taking place. And gamma radiation is a big part of outer space, which is why traveling in space can be quite dangerous because of all that excess radiation. Why, um, when we travel to space, there's a lot of extra equipment that has to go into it in terms of not just keeping people safe from the different types of atmospheric pressure kinds of considerations, but also the radiation that they could encounter while in space. Now, for the most part, gamma radiation can be absorbed by gases in our atmosphere. And that's how we encounter most of it on Earth. What we've been able to see is that gamma rays can be used as part of radiotherapy, radiation therapy for cancer cells, which is one of the reasons why it is used in that way. But the thing that's dangerous about them is obviously if you don't have cancer, it can also disrupt your normal cells. And that can ultimately lead to cell mutation, cell death, or even in other circumstances, those cell mutations that can become malignant and potentially cancerous. In terms of penetrating power, what we mean by that is how well does your body block these different types of radiation? For the most part, alpha particles can be blocked by your skin. And so alpha particles and alpha radiation don't pose a whole lot of threat to you unless you ingest them, unless you inhale them in some kind of way. Once they break through that external layer of skin and clothing, they can do some pretty significant damage to your internal organs. But like I said, you have to intentionally take a sample of it, which is unusual. Beta particles, on the other hand, are able to penetrate your skin. But materials like paper, aluminum, small thicknesses of lead, obviously, can block their penetration. The issue with beta particles is that they're ionizing in nature. They will strip electrons off of things that they interact with. And that's ultimately what causes a lot of the cellular issues that we see with alpha particles or with beta particles. Now, as I mentioned before, gamma radiation is the most penetrating, has the most damage potential. While a lot of gamma radiation is absorbed by our upper atmosphere, down here, without the thickness of our atmosphere to kind of protect us, you need a pretty dense material to block gamma rays, and usually that dense material is lead. There are some occasions where if you have a significant thickness of concrete, concrete will also do the trick as well, which is why if you pay attention in terms of if you've ever had an x-ray taken, the x-ray, the technician will always run behind a wall to take the picture. So, you know, they'll take a picture of your shoulder and they'll say, okay, hold still. And they'll set the machine in motion, and it has a couple of second delay, which is long enough for them to run behind you or to the safe area behind usually a decent thickness of concrete. And that would be true for x-ray machines or, you know, any other kind of imaging that you'd have to take. There's usually a barrier between the patient and the person that is operating the machine, and it's for their safety. So pictorially, we can see that, again, alpha radiation is usually blocked by your skin. Beta radiation will go into your tissues and can potentially cause damage there, but is unable to penetrate your bones and into your organs unless it comes in through another mode of entry. If it just is hitting against your skin, it doesn't do a whole lot of anything. Gamma radiation can penetrate through everything, and that's why it's the most dangerous overall. So let's take a look at a couple of examples of these kinds of transmutation reactions. And let's write some balanced equations. So we're told we have polonium-218. Polonium-218 undergoes both an alpha decay and a beta decay. So let's look at the reactions that work for these. And so what I have is 218 polonium, and polonium has an atomic number of 84. Now, if it undergoes alpha decay has an atomic mass of 4, an atomic number of 2, and the Greek letter alpha as its symbol. Now, if you put here in this place 4 to helium, that is widely considered to be acceptable as a way of showing alpha decays, because alpha decays do represent helium nuclei. You could do it in either way, if you so chose. We'll keep it the more conventional way for now. Now, to figure out the daughter nucleus here, we're going to have to look and do our subtraction. 218 minus 4 is 214. 84 minus 2 is 82. And element number 82 is lead, Pb. So this is the equation for the alpha decay of polonium. Now for the beta decay, I could do the same thing, 218 and 84 for my polonium. Undergoing a decay. Atomic number for beta particle, or excuse me, mass number for the beta particle is 0. Atomic number is -1. And so I can either show that as an electron E, or I can draw in. Okay. All right, lesson learned there. So -1 is the atomic number for my beta particle. And I can use the same kind of things. 218 minus 0 is going to give me 218. 84 minus -1 would be 85. Atomic 85, correct me if I'm wrong, that's astatine, AT. And so that's all there is to that. So like I said, transmutation reactions are relatively easy. It's just a matter of when it comes time to figure out the missing piece, if I have the right particle, it's a matter of adding and subtracting. The numbers on this side have to add up to the numbers on this side, and vice versa. And so if I have a particle that's missing on this side, I can subtract to figure out what it is. Any questions?
No.
Okay, so I'm going to ask you to walk me through this one then. So I've got two different nuclear processes here. Can we solve for the missing particle, and can we tell what the nuclear process is?
Okay. So AC's atomic number is 89.
Okay.
And then the FR would be 87.
Okay, so far so good.
Meaning it's the alpha.
Okay. Yeah. So 4 to alpha nuclear process would be alpha decay. Okay. So far so good. All right, let's go through the other one.
V is atomic number is 23. And I believe it's beta. So therefore that TI would be 24.
Okay. Do you have your periodic table up?
Yeah. Wait.
Okay, what's the atomic number of titanium?
84. I mean 81. I don't know why I said that. It's 81.
For titanium? No. Ti.
Oh,
Should
I'm
be
looking
very,
at the wrong thing. I'm looking at TL.
yeah.
TL is 22.
Okay. So TI is 22. Okay.
Oh,
So,
it's the electron one. Electron capture.
right, so the big thing to look for is look where this blank is. It's on the reactant side. It's not on the product side. So I've got a 0, a -1. Um, so this is your electron capture. Yeah, so it's really important. You can't jump to conclusions just because of what you think it might be. You've got to pay attention to the details sometimes. And so the dead giveaway, so to speak, in this case was the fact that the blank here, the missing particle, was a reactant, and we already have a parent and a daughter. The missing particle being a reactant meant it had to be electron capture. Um, if this was on the other side, then we would be talking for titanium, we'd be talking about positron emission. Because to get 23 to 22, I would have had to emit a +1 charge. Right. Any questions?
No.
Okay. All right, let's do some more then. Radon 222 decays with a loss of an alpha particle. What is the balanced equation for this decay? So walk me through it.
So, you put radon and then the 22 at the top. And then radon's atomic number is 86. RN is 86, right? Yeah.
Yes.
Um, and so then you put the alpha particle 4 and the 2. So therefore it will be 218 and then 84. And that would be PO, polonium.
Correct. Okay, so far so good. Next one. What is the product nuclide formed by the beta decay of tritium? Tritium is one of the stellar isotopes of hydrogen. Doesn't exist a whole lot here on planet Earth, but it's relatively common inside of stars. There it is.
Okay. So it's beta, so therefore the 0, -1. Meaning it will be 3 and I believe 2. So it would be helium.
Yep, that's correct. Okay. All right, sounds like you've got it. All right. So the last thing that we need to talk about is the idea of rates of decay. Now we've talked, radioactive decay is that spontaneous disintegration. Thing about spontaneous is it doesn't mean that it's rapid. Spontaneous just means that it occurs on its own. And so if you have to take Chem 2, you'll learn a lot more about spontaneous reactions and non-spontaneous reactions when you learn about thermodynamics. Spontaneous just means that it occurs. It occurs on its own. It doesn't have any outside influences impacting it at all. And when it comes to spontaneity, radioactive decays are spontaneous. What's also interesting about them, though, is that they all decay at a very measurable and constant rate. We call that rate a half-life. So the half-life of a radioactive decay is the amount of time it takes for half of the materials, half of the radioactive particles to decay. So let's say that I have a 50-gram sample of my radon 222. The half-life would be how long does it take for 25 of those 50 grams to actually decay. And what's interesting about half-lives and nuclear decays is that the half-life is consistent regardless of the amount of sample present. And the reason that's important is because from the standpoint of being able to determine how long a sample's been around, we can use radioactive decay to actually kind of figure out that idea. It's called radiocarbon dating, where we can use the fact that the half-life does not change based upon quantity to estimate how long things have been around. And the way that we do that is if we know how long has passed and we divide that by the amount of half-lives, or excuse me, the half-life of the material, we can know how many half-lives have passed. Now, in radiocarbon dating, what we do is we kind of flip this equation around. We're trying to figure out how long this thing's been around. So what we do is we say, okay, we can figure out how many half-lives have passed by comparing the sample of something that is no longer living, that is an ancient artifact, compared to the amount of carbon that is in a living sample. That'll tell us how many half-lives have passed. And then we multiply that by the length of the half-life, and that gives us an idea of how long ago something died, when, from what era was this particular artifact from, that kind of thing. So when it comes to calculating half-lives, we can calculate the half-life, the amount that is left over, by simply taking 1/2 and raising it to the power of n, the number of half-lives. And so after 1 half-life, we'll see that half of the sample is remaining. After 2 half-lives, we'll see that 1/2 squared, or 1/4 of the material is remaining. After 5 half-lives, we'll have 1/2 to the 5th, or 1/32 of the sample remaining. And so, again, what's really cool is the consistency of this. So the curve appears to be slowing down in terms of, the amount that is left over. But what we're seeing here is that on each step of the journey, half of the remaining sample is what is disappearing. So I started with 40 here. At the end of the first half-life, 20 of them have converted. After the second half-life, only 10 more converted. That was half of the 20 that were there. After the third, we're down to just 5, but again, that was half of the 10 that were there. And where this is really interesting, where this gets used, again, is in this concept of radiometric dating, where we can compare an object, and depending on, and looking at
2 slides real quick.
You want me to go back?
Yeah.
Okay.
Yeah, that one. Okay, sorry.
Okay. All right, you're good now?
Yeah, I'm good. Thanks.
Okay. Okay, so with the concept of radiometric dating, most often this is used for carbon, where, because most artifacts, most things that we find are derived from living things. And so we know that, living things like trees, which make up wood, which can be, passed down, or, living things like human beings, which are carbon based also. What we can take advantage of is the fact that when things are living, they are constantly cycling in and out carbon. And so you have a small amount of radioactive carbon in you right now. It's just a natural byproduct of the fact that on average, um, on average, most of the carbon that you ingest, that you take in, and that you exhale is carbon 12, which is not radioactive. But roughly 0.01% of the carbon that you take is carbon 14, which is radioactive. Now, carbon 14's radioactivity is nothing that's going to really harm us. It's a beta emitter. It's a relatively slow beta emitter, on the order of a couple thousand years, for a half-life. But while you are alive and taking in nutrients and expelling nutrients, you are constantly cycling carbon in and out of your body. And so the amount of carbon 14 in your body is relatively a constant level. And so when you expire, you're no longer exchanging that carbon. That carbon starts to go down, and you start to decay from a radiometric standpoint, the carbon 14. Well, in 20,000 years, when they dig up our civilization and find out how we lived, what they can do is they can compare, okay, this is the amount of carbon 14 in our bodies now as living beings. This is how much carbon 14 we found in that sample. And comparing those two to each other, we can figure out how many half-lives have passed. And based on that, figure out how long it's been since we died. And that's kind of in a very rudimentary sense. That's how radiocarbon dating works. And so there are a number of ways of going about doing that. Like I said, carbon's probably the most common. There are other radiometric techniques out there. One of them is known as the Rutherford Helium method. We can use mass spectroscopy to very quickly analyze how much, if I'm looking at the carbon in the sample, how much of it is carbon 12, how much of it is carbon 14, to get an idea of how much is present there. And so, like I said, the way that they can do this ultimately is, if they know the amount of starting material versus the amount of carbon material at that time, they can use this equation to find out how much time has passed. And that's essentially what this is doing. And so obviously human samples are part of that, but anything that's carbon based can be derived from this technique.